Okay, so I already finished yeah reading the exam 2. Okay, so if you have any questions, okay, so yeah, I have office hour just right after this class. Okay, so yeah, you please log in back here to Zoom. Okay, right. So today we continue chapter 14. Okay, yeah, if you have any questions, just type in the chat window. Okay, right. So last time we talked about the this equation, okay, so we tell you what kind of the frequency you can see for certain the nucleus, okay, so also atom, okay, right. So here, okay, so this gamma, okay, so that's the geromagnetic ratio, okay, so this one is kind of only relate to the atom, okay, so different atom has the different gamma value. Okay, so that's why you get kind of different kind of position, different kind of frequency. Okay, so for the NMR. Okay, and also NMR frequency relate to external magnetic field. Okay, higher external magnetic field. Okay, and then you have higher frequency. Okay, and then definitely higher energy. Okay. Right, so that's why kind of when people talk about any market or talk about kind of 60 megahertz, okay, 300 megahertz, okay, or kind of 400 megahertz, okay. So that's actually talk about kind of how strong of the magnetic field, okay. So yeah, this one, okay. But if you use megahertz, okay, so that's easier to understand, okay. So that's converted the magnetic field kind of strong to a frequency, okay. And so if you have higher the magnetic field, okay, so higher frequency, okay, and then the energy gap between the alpha and also beta state, okay, so the bigger, okay, and then you have kind of the more different in their kind of population, okay, and you have higher kind of the intensity in their signal, okay. So that's one advantage of a high frequency NMR, okay. There are some other advantage, okay, so I will talk about it later, okay. So in the chemistry department, okay, so in organic lab, okay, so we have 60 megahertz NMR, okay. So probably we'll learn how to use it like maybe 3 weeks later, okay. Yeah, learn how to use kind of record the proton NMR and also carbon NMR, okay. And in the chemistry department, okay, we also have one 400 megahertz NMR, okay. So so that's pretty powerful, okay. Mainly dedicated for the research, okay. So yeah, if you have a chance, you can take a try to use it. Pretty nice one. Okay. So normally for low frequency NMR instrument, okay, so the 60 megahertz, okay, so just use normal magnetic, okay. So but for the high frequency like 300, 400, okay, so normally you have to use superconducting kind of magnet, okay. So that's one you need to use the liquid nitrogen and also liquid helium, okay, to make it functional, okay. Right, here's kind of the basic setup here of the NMR instrument, okay. All right, so we have the magnet, okay, so in these directions, okay, and then let's apply some external magnetic field, okay, and this here the blue coil, okay, so that's the strike the sample, okay, with the radio frequency, okay, and so this here this is here the sample tube, okay, so NMR tube, okay, so normally you dissolve your sample in some NMR solvent, okay, and then you can record the NMR sample for this you record the NMR spectrum for this sample, okay. And this red coil is kind of receiving the coil, okay. So record the once the sample, okay, so go back to ground state, okay, so release some kind of radio frequency that can be recorded by this red coil, okay, and then convert to into some computer and then give out kind of the NMR signals, okay. And this one kind of the setup for superconducting magnetic kind of NMR instrument, okay, so high frequency one, okay. So because for the superconducting magnet to work, okay, so you have to cool it in liquid helium first, okay, and close to absolutely 0 degree, okay, and then outside of liquid helium, okay, the layer of the liquid the nitrogen have to kind of cool down, okay. So that's why the high frequency the NMR instrument is quite huge, okay. So normally, okay. All right, okay. So we talk about a lot, okay. So here show you real kind of the proton NMR, okay. So what it looks like, okay. So I also draw one, okay, here, okay. All right. So for the proton NMR, okay. So for the x-axis, okay. So that's here chemical shift, okay. Yeah. So the chemical shift case with the unit is the ppm, okay. Right. And interesting kind of the different from other the scale, okay. So the for any market, 0 is on the right, okay. Here that's 0, okay. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. So normally from 0 to 10, maybe a little bit extend out for both ends, okay. And so for the y-axis, just kind of intensity, okay, but normally you don't need to label it, okay, because the peak signal kind of strength will be labeled by integration, okay. So we'll learn that later, okay. Okay, and so normally speaking, there's the one signal at 0 ppm, okay, small peak, okay. That's the TMS, okay, so peak, okay, so that's internal standard, okay, so you add into the sample solution, okay, so theoretical kind of instrument, okay, that's 0 signal, okay. And then you see some kind of other peaks, okay, so so depends what sample, okay, so for example, you may see kind of the doublet, okay, so here, okay, so that's one single, okay, and maybe see kind of the triplet, okay, triplet kind of 3 peaks. Yeah, so nothing, okay. So for this sample, totally 2 signals, okay. Right, so that really depends how many different different kind of the proton in one molecule, okay. For example, okay, so here this is the protonema of your benzene, okay. Benzene only has one kind of proton, okay, so that's all same, okay. So that's why only show one signals, okay, one signal, okay. Right. So now come kind of some special words, okay, for the describe the chemical shift, okay. So for the lower number of the chemical shift, okay, so we call kind of high field strength, okay, so high field, okay, so and the higher number, okay, so we call kind of low field, okay, so strength, okay. And so if some reaction happen or some kind of temperature change or kind of pH change, okay, so the signal will shift, okay. So if shift to the lower number end, okay, we call kind of upfield shift, okay. So that's those means those proton get kind of more shielded, okay. If it's shift to higher number end, okay, we call downfield shift, okay. So when I was a student, I get kind of quite confused, okay. So looks like the going up, you go in kind of small number, and when you're going down, goes kind of the higher number, okay. So actually I'm still confused now, okay. So in this case, most time I just see kind of the higher chemical shaped cases, higher chemical shaped and low chemical shaped case. So that's just some kind of the traditional way to describe the chemical shaped case. Right, just keep in mind, okay, so each distinguished kind of the chemical hydrogen, okay, so we'll show one unique signals, okay. So if in one molecule there's more than one kind of the kinds of the protons, okay, so you see kind of more than one signals, okay. Right, okay. So what kind of information can be provided by protonema, okay? So that's a lot of information actually, okay. Let's show them one by one, okay. First kind of number of proton signals, okay. That's can tell kind of how many the different kind of the protons, okay. We call chemical kind of distinct proton. For example, here's the 3 pentanone, okay. So for 3 pentanone, okay, although there are kind of the 2CH3, okay, and then 2CH2, okay, but only show 2 signals, okay, because this 2CH2, okay, 2 blue one, okay, the 2CH2, okay, they are kind of same, okay, so that will show kind of same chemical shape, okay. Same thing for this 2CH3, okay. So those also kind of symmetrical to each other, okay, and then same chemical environment, okay. So they also show the kind of the same signals, okay. So that's why you saw kind of 2 signals, okay. Yeah. So number of chemically distinct kind of protons, okay. Right. Second information kind of these 2 signals won't be same, okay. So they show kind of different positions, okay, on the NMR spectrum scale, okay. And so these we call kind of chemical shift positions, okay, on y-axis, okay, x-axis, okay, and tell kind of what kind of environment, okay, what kind of carbon, okay, hydrogen, okay, bonded, okay. So for example, okay, so the blue one, okay, CH2, okay, so close to carbonyl, okay, so that's the little bit strong, yeah, inductive factor, okay, so yeah, de-shielding, okay, so those yeah we'll talk about later, okay, so don't worry, okay, so that's why it has higher chemical shape, okay, but the red one, okay, so yeah, nothing, okay, just kind of yeah, CH2 next to it, okay, so that's yeah, lower chemical shape, okay. Right, and then for these yeah, for any mark, okay, so yeah, quite often you see kind of yeah, some curving, okay, some curve, okay, just by individual yeah, just yeah, peaks, okay, individual signals, okay, and also quite often you see some kind of numbers, okay, by this curve, okay. So sometimes kind of number you put underneath of yeah, the peak, okay. So that's yeah, actually kind of yeah, the yeah, integration, okay, so integral kind of area, okay, for the peaks, okay. So yeah. And so this integration, okay, so actually the proportional to the number of your protons, okay, right? So for example here, okay, so for 3 pentanone, okay, so we have 4 this CH2, okay, blue proton, and 6 this the red kind of protons, okay, CH2, 2C3, okay, and then the integration ratio for these 2 signals, okay, will be 2 to 3, okay, so that's relative ratio. Kind of it's proportional to the kind of number of protons, okay, very useful information, okay. And the fourth information kind of I guess some of you already noticed, okay. So yeah, for NMR signal, okay, so quite often showed kind of split peaks, okay. So for example, this red one is kind of triplet, we call kind of 3 peaks, okay, and this blue one are kind of 4 peaks, we call kind of quartet, okay. So that's called kind of multiplicity, okay. Y ratio is 2 to 3, okay. All right. Do here. All right. Okay. So for the blue one, okay. So I use the blue color, okay. Represent kind of these 2 protons, these 4 protons, okay. All right. And then the red signal, okay, represent kind of this CH3, okay. All right. Okay. So we have totally the 4 blue proton, okay, and then versus kind of totally 6 red, okay. So that's a relative ratio kind of equals 2 to 3, okay. So the integration area relative ratio equals to the number of your proton ratios, okay. So that's here, okay. Yeah. Right. So for the multiplicity, okay, so tell you the information about your nearby kind of your protons, okay. So I'll talk about that later, okay. Yeah. Right, so we'll go through this 4 information one by one, okay. First is the chemical shift, okay. So chemical shift actually kind of the independent of the extramagnetic field, okay, strength, okay. So maybe bring here, okay. So sometimes kind of okay. So if we in the 400 megahertz magnetic field, okay. So higher one, okay, and then this one, the frequency chemical shift, okay, frequency just chemical shift, okay. So will be kind of higher, okay. If you kind of lower 160, also this one will lower, okay. So in this case, for the same proton, okay, okay. So at a different instrument, okay, will show kind of different kind of the chemical shape, okay. That's kind of quite messed up, okay. But we can use kind of a certain equation, okay. So convert to kind of all the frequency into a chemical shape, okay. That's make it all the same proton showed kind of same chemical shape, okay. So even at a different instrument, okay. So how do we do that? Okay, so first we add a little bit the TMS, okay, that's internal standard, okay, into the solution, okay, your NMR solution, okay. So TMS is the tetramethylsilane, okay. So the protons, okay, all the 12 protons, okay. So in the tetramethylsilane, okay, show kind of 0 ppm, okay. So that's here, this guy, okay. So then all other kind of the proton kind of chemical shape, okay. So use this one as reference, okay, and then shift downfield from kind of TMS, and then times kind of 10 to 6, and the whole thing divided by kind of the instrument frequency. That you get kind of chemical shape, okay. Okay, so maybe write you guys again, okay. So this equation, okay, so you just a little bit keep in mind, okay. So that's help you kind of the determine the chemical shape, okay. But actually in exam, okay, we won't do kind of any calculations, okay. So this. Yeah, so that's observe kind of a peak frequency, okay, from TMS, okay. So that's relative kind of ratio, okay, and then this one times 10 to 6, okay, and then divided by instrument kind of the frequency, okay. Right, so in this case, even under different kind of instrument, okay, so 60 megahertz, okay, or 600 megahertz, okay, so all give kind of same chemical shape for the same kind of protons, okay, so that, and shielded and deshielded, I will explain later. That's just kind of some important words, okay. And chemical shape, okay, so normally we use this delta, okay, indicated, okay, so unit I already set kind of ppm, okay, shielded, deshielded, I will explain later, okay, don't worry, okay. Right, so just keep in mind, okay, I'm just going to measure kind of how far signal from kind of the TMS signals, okay, so relative ratio, okay. And also, based on this kind of equation, okay, so you can change kind of the big number into kind of small number, okay. So otherwise, you already use kind of 100 megahertz, okay. So that's kind of too big, okay. So you divide kind of times 10 to 6 divided by kind of harmful for instrument that kind of 0, 1, 2, 3, 4, 10, okay. So that's much easier kind of remember it, okay. All right, okay. So now we come kind of shielding or deshielding, okay. So theoretically speaking, okay, so for all the proton, all the hydrogen, okay. So they should show same kind of chemical shape, okay, because it all depends on the gamma, okay, and extramagnetic field, okay, so cancel out, okay, by this equation, all right, so that should be same, but if the different kind of proton, okay, so like this the 3 pentanone, okay, so so these two kind of different, okay, why they have kind of different, okay, because the different proton, okay, they have kind of different chemical environment, okay, so so in reality, okay, in addition to extramagnetic field, okay, there's some kind of local magnetic field, okay. So where does this local magnetic field come from? Okay, it comes from the electrons in carbon, hydrogen, or other atoms, okay. So for example, okay, so if we look at kind of this CH3, okay, so this CH3, okay, so the carbon has some electrons, okay, and then nearby the carbon also has electron, and also nearby hydrogen also has the electrons, okay. So all these electrons, okay, generated we call the local magnetic field, okay. So so this local magnetic field, okay, so normally kind of the opposite direction from external magnetic field, okay. So that's here. So that's external, okay. Local magnetic field kind of much smaller, okay. So called kind of B local, okay. Right. So that's you cancel out the sum of external magnetic field, okay. So because the different carbon, okay, different hydrogen have different kind of local environment, okay. They have different kind of the local magnetic field, okay. Then they see the cancel out kind of the extramagnetic field, okay, different kind of extent, okay. So that's they have really different kind of we call the effective the magnetic field, okay. So they have different effective magnetic field, they have kind of different kind of chemical shapes, okay. So that's we call kind of where they have kind of different kind of shapes, okay. And so if molecule kind of said to be shielded, means kind of shielded from kind of extramagnetic field, okay. So you cannot hold extramagnetic field, okay. So because cancelled by kind of local magnetic field, okay. Right. So here's just keep in mind, okay. So different kind of the protons, okay. So they have kind of different kind of electron distributions, okay. They have different kind of local magnetic field, okay. And then they will show it to different extent, okay. So look at kind of this example, okay. So this is the propanoic acid, okay. So 2 protons, okay. So this oxygen proton, okay. So connected by oxygen strong electron withdrawal group, okay. So not too much shield, okay. But this proton, okay. So on alkyne, okay. So close to a lot of pi electrons, okay. Strong shielding, okay. So that's why these 2 protons a big difference chemical shape, okay. So alkyne has much the lower chemical shape, and then acid proton has much higher chemical shape, okay. So go more detail, okay. So the 2 factor affect here the chemical shape, okay. So chemical shape, okay. So the shielding, okay. So one kind of inductive effect, okay. Another called kind of pi electron effect, okay. So we talk about them one by one, okay. Right. So first inductive effect, okay. So we just compare all of these C3, okay. So they touch on different atom, okay. So if you take a first look, you find kind of if this C3 attach kind of the stronger electron rejoin group, okay, or kind of more electronegativity atom, okay, then higher chemical shape, okay. So that's easy to understand, okay. So if you have kind of stronger kind of negative atoms, okay, the poor electron weight, and then you have a smaller kind of the local magnetic field, okay, and then you have kind of we call the de-shielding effect, okay, and then you have kind of higher chemical shape, okay, and then this goes same trend as kind of the atom the electromagnetic electron the negative kind of effect, okay. And for example, okay, fluorine has kind of the highest kind of electromagnetic, highest kind of electronegativity, negative kind of effect, okay? And then this C3 has higher chemical shape, okay? And when we go to this here, when we come to kind of carbon, okay, carbon very weak the small electronegative, okay, and then there's very weak kind of inductive effect, okay, and then that's why for the saturated kind of alkane normally the C3, okay, so has a pretty low chemical shape, okay, and definitely lowest ones the silicon, okay, silicon because it's even poor the electromagnetic electronegative kind of effect than the carbon, okay. All right, so shielded means kind of electron rich, okay. So shielded generates more kind of local magnetic field, okay, and then that's we call it shielded, okay, right. And de-shielded kind of means kind of electron poor, okay. So you normally connect with the electron rich group, okay, or maybe kind of connect with the electron high electronegativity atoms, okay. So poor electron weight, okay, so that's kind of the high chemical shape we call it de-shielded, okay. So that's shielded, de-shielded means, okay. All right, just one thing, please keep in mind, okay. So you also can write it down, okay. So for the different types of the hydrogens, okay, so primary hydrogen, secondary hydrogen, and tertiary hydrogen, okay, so they may have kind of a little bit different in their chemical shape, okay. So that's the primary hydrogen, okay, C3, okay, so has a lowest one, okay, and then followed by secondary CH2R, okay, and then followed by kind of the tertiary, okay, CH R2, okay. So R is alkyl group, okay. So why it's like that, okay? Because the carbon has a little bit higher electronegativity, okay, compared with the hydrogens, okay. So that's why the tertiary has 3 carbons, okay. I mean the carbon has a little bit higher electronegativity compared with kind of hydrogens, okay. So the tertiary has the 3 carbons, okay. So little bit higher the electronegativity, okay. So that's higher chemical shape, okay, and then followed by secondary, okay. Tertiary, just 3 hydrogen, okay, only 1 carbon, okay. So that's has a low the electronegativity, okay. So little bit keep in mind, okay, because help you kind of distinguish kind of primary hydrogen, secondary hydrogen, and tertiary hydrogen. Okay. Primary normally lower than 1, okay. So chemical shape, okay, and then secondary 1.2 and tertiary 1.6, okay. So a little bit keep in mind, okay. Right, and then next, the pi electron effect, okay. So pi electron effect kind of quite the significant significantly influence kind of the chemical shape, okay. So we do the comparison here, okay. So aldehyde kind of sealed up on the pi electrons there, okay. Chemical shape kind of the 10, okay. So for the aldehyde proton, okay. For the aromatic protons, okay, so around like 7, okay. So for the alkene proton, okay, so around like 5, okay. Interesting for the alkyne, okay, so proton kind of around 1.8, okay, much smaller than another 3, okay. So these 3 we call kind of de-shielded, okay, so downfield shaped, okay, higher chemical shaped, okay. And last one we call kind of shielded, okay, goes kind of higher, lower chemical shaped, okay. So why is that, okay? Because the pi electrons, okay, so it's kind of much electron rich, okay, can generate kind of very strong kind of local magnetic field, okay. And this local magnetic field, okay, if it's kind of aligned with extramagnetic field, okay, so that's will reinforce, okay, so you see kind of downfield shaped, okay. If you kind of opposed to kind of extramagnetic field, okay, so you see kind of the shielded effect, okay, and then goes kind of the lower chemical shape, okay. Right, so we'll do it one by one, okay. First, aromatic kind of compound, okay. So for the aromatic compound, okay, totally, benzene has the 6 pi electrons, okay. So that's we learned in the previous chapters, okay. So there are kind of the 6 p orbitals, okay. Each orbital has 1 pi electrons. Right, And those pi electrons, okay, so form very strong kind of local magnetic field, okay. So it's kind of a very strong circle, okay. And then this magnetic field, okay, quite interesting, okay. So inside of the bending ring, okay, inside of bending ring, okay, so opposite direction from your external magnetic field, okay. So magnetic field external kind of this one, okay, and then this inside, okay. But outside, okay, same direction as the external magnetic field, okay. And for the proton on the bending, okay, so it's on outside of the ring, okay, definitely, okay. So that's why the proton on bending, okay, can feel actually the magnetic field, okay. So that's reinforced, okay. So then that's very strong de-shielding effect, okay, and then that's why proton chemical shape is quite high, okay, 7 to 8, okay. And similar thing for the alkene, okay, sorry, okay. Alkene, okay, so only 2 protons, okay, so alkene, okay. Only 2 protons, okay, generate a little bit smaller kind of local magnetic field, okay. This local magnetic field also the inside of the bond, okay, so the opposite direction from your external magnetic field, okay, so external, okay, and inside kind of the opposite, okay, but outside, okay, same direction, okay. And then for the hydrogen on alkene, okay, so normally it's just kind of outside, okay. So that's why it get kind of actual magnetic field, okay. So from a local magnetic field, okay. And then that's why kind of de-shielded, okay. So and then alkene chemical shape is kind of about 5 to 6, okay. And then come kind of aldehyde, okay. Aldehyde has a huge kind of very high kind of chemical shape, okay. 9 to 10, okay. So why is because the pi electron effect, okay, so similar to alkene, okay, so this cell bond pi electron generating local magnetic field, okay, so the hydrogen on the outside, okay, so reinforced kind of magnetic field, okay. Another reason, okay, so because the carbonyl group, okay, is the electron withdrawal, okay, strong de-shielding effect, okay, so that's because these 2 reasons, okay, so that's make the aldehyde proton, okay, this proton, okay, has pretty high kind of chemical shape, okay. All right, so now come to alkyne, okay. So alkyne, okay, so certainly also generates the strong local magnetic field, okay. So but the interesting is for the proton, okay, so that's proton, okay, so on alkyne, okay, so somehow located at the same direction of the opposite direction of the local magnetic field from the external magnetic field, okay. So somehow like this, okay, go like this direction, okay. So opposite direction, okay, so the external magnetic field go this way, and then local magnetic field go this way, okay. So that's cancel out some of the external magnetic field, okay, and then that's we call it shielded, okay. And that's why our kind of the proton has a much lower kind of chemical shape, okay. Right, and then in addition is kind of the hydrogen on helium atom, okay, helium atom kind of the nitrogen, oxygen, sulfur, something like this, okay. So those the chemical shape, those proton, okay, so quite kind of the unique, okay. So really depends kind of the sample concentration, temperature, and pH, okay, and depending on the kind of hydrogen bonding, okay. So and here's one example, okay. So for this is the propanol, okay. So 4 kinds of protons, okay. So OH kind of blue one, green one, and red one, okay. So should show kind of 4 different peaks, okay. 4 different peaks, okay. And so for the OH, because there's a lot of change, okay. So that's the OH proton, okay. So not the very fixed kind of chemical shape, okay. So defined chemical shape, okay. So can be from 2 to 5, okay. So depends on the concentration, temperature, and the pH, okay. Same thing for NH, okay. So could be from 1 to 3, okay. And then for the capacity kind of proton, okay, so it's from 10 to 30 because capacity has a much higher kind of the electron withdrawing effect, okay. All right, and one unique thing about those heater kind of the atoms, okay, bonded the protons, okay, so they have relatively broad peak, okay. Okay, so that's clearly show here, okay. So for the all other the CH protons, okay, so relatively sharp, okay, but the OH proton kind of broad, okay, because that's kind of quick exchange, okay. So you can lose gain, okay. So that's a little bit keep in mind, okay. So because help you identify that's OH protons, okay, in future. All right, okay. So similar to the IR spectrum, okay, so the different for IR, okay, so different bond, different function, okay, they have different wave numbers, okay, so different kind of signals, okay. Protons also similar thing, okay, so depends what kind of chemical environment, okay, so different protons show different position in the proton number, okay. The lowest one is the saturated kind of the hydrogen, okay, carbon, okay, so those like alkane, okay, so because there's the no kind of electron withdrawing effect, okay, also no pi bond effect, okay, and then followed by kind of allylic and also this the carbonyl connect kind of the protons, okay. So those has a little bit electron withdrawal effect and those the pi bond electron kind of the effect, okay. So it has a little bit higher chemical shape, okay. And then followed by kind of the heteroatom connect kind of the actually kind of this heteroatom connect carbon and then connect to this hydrogen, okay. So that's because of the inductive effect, okay. So have a higher chemical shape, okay. So normally about 3.5 or something, okay. And then followed by alkene proton, okay. So that's the hydrogen directly attached to the theta bond, okay. Very strong pi bond electron, and then effect, okay, and then has the higher chemical shape, okay. So make sure you see the difference between the allylic and also vanillic, okay. Vanillic protons cannot directly attach kind of the theta bond, okay. Allylic is separated by one carbon, okay. So you see kind of they have big difference in their kind of chemical shape, okay. And next comes kind of the aromatic proton, okay, so normally around 7, okay, so because kind of the strong pi electron effect, okay, and then followed by the aldehyde, okay, so around 10, okay, eventually kind of capacity, okay, around like maybe 11 to 13, okay. Okay, so so although okay, so you can use the IR table, okay, so show you kind of the IR table, okay. All right, so I already uploaded the two proton okay, proton tables online, okay. So this is the first one, okay, showed you kind of different proton chemical shapes, okay. Pretty good one. And then there's the second one here. So this one kind of give a little bit better view, okay, but the last the proton chemical shaped, okay. So you are allowed to use these two chart, okay, for the future exam quiz, okay. So although you can bring this chart for your future exam quiz, okay, but a little bit keep in mind what kind of proton at what area, okay. For example, okay, so I know aldehyde should be around 10 and the aromatic proton should be on the 7, okay. So that's will save you a lot of time, okay, during exam the quiz, okay. That's please keep in mind. All right, okay, so that's a lot of theory, okay. So now we move to hard part, okay. So if you fall asleep, okay, so please wake up, okay. So keep a little bit alert, okay. So now we move to very kind of the important part, okay. Also most challenging part of this chapter, okay. Number of signals, okay. All right, so that's the top of kind of equivalent hydrogen, okay. So chemical equivalent hydrogen cannot have same chemical shape, okay. So they have same chemical environment, okay. So I like to use kind of chemical environment, okay. So how do you so for example, okay. So we already know that for the propanol, okay. It's right here. All right, so this one, okay. So so this CH3, okay, has different chemical environment from this CH2. This one also from this different chemical environment from this CH2, and also eventually kind of the OH, okay. So all those kind of the CH2, CH3, OH have different chemical environment, okay. So that's why for the propanol you see 4 signals, okay. And then for the this the 3 pentanol, okay. So although the 4 bunch of protons, okay, but only see 2, okay, because this CH2 and this CH2, okay, same chemical environment, okay. Same thing for this the CH3 and this CH3, okay, same chemical environment, okay. So that's why only show 2 signals, okay, for this here, okay. So that's we call kind of the chemical equivalent, okay. These two chemical equivalent, okay. All right. So next come kind of the things, okay. How do you determine kind of the two protons are chemical equivalent or have same chemical shape, same kind of the chemical environment, okay. Right. So 2 ways to do it, okay. the first way kind of to see whether these two hydrogens relate to by the rotation axis, okay, or kind of simply plane, okay. So if they are related by the rotational axis or simply plane, okay, then these two protons will be have same chemical shape, same kind of the chemical environment, and also called chemical equivalent. Okay. For example, this is the one boron butene, okay, and then the two hydrogen on the CH2, okay. So you can relate by simply plane, okay, the pass through whole molecule, okay. So left kind of HA is kind of mirror image into HB, okay. So that's called simply plane, okay. And then these two protons will have same chemical shape, okay. Right, and then next one, okay. So it's the two 1R2R kind of 1,2 dimethyl cyclohexene cyclobutene, okay. So for HCHD, okay, so relate by rotation axis, rotation axis pass through kind of middle of this bond, okay, and also this middle of this bond, okay. So something like this. Right. And then you just rotate this rotation axis, okay, like 180 degrees, okay. So exactly got same molecule, okay. So HD will go here, HC will go here, okay. So that's we said kind of HC, HD related by rotation axis, okay. These two have same chemical shape, okay. So that's how do we determine one molecule is kind of or two protons same chemical shape or not, okay. Right. Here are more example, okay, and I bring back here the annotation again, okay. Right. So for these two protons, okay, have same chemical shape, okay, because they are related by both rotation axis, simply plane, okay. So all cut through here, okay. And same thing for the these two protons, okay. These two protons related by rotation axis, simply plane, okay. So the simply plane cuts kind of the two fluorine and this carbon, okay. And rotation axis just goes through like this. Right. And then it's kind of these two have same chemical shape, okay. Similar thing for here, okay. So these the two protons, okay, on the kind of this triangle, okay, also have same chemical shape, okay. So the rotation axis, okay, pass through like this, and the simply plane pass through kind of this triangle, okay. All right, and then for the this molecule, okay, these two protons have same chemical shape because they are related by simply plane, okay, only simply plane for this case. This simply plane pass kind of this fluorine, chlorine, and also this carbon, okay. Something like this, okay. And then mirror image to each other, okay, simply plane, okay. So rotation axis kind of for example here, okay. So just draw here, okay. And then you rotate kind of 180 degrees, okay. So you generate kind of same molecule, okay. Have to same molecule. That's means rotation axis, okay. I'll give you one example, one more example, okay. And they see also related by the simply plane, okay, castle kind of this triangle and this carbon, okay, and then these two carbon, these two hydrogen have same chemical shape, okay. All right, so here kind of these two highlighted proton relate by rotation axis, okay. So how do you determine the case? So so that's here. This rotation axis pass through kind of the middle of the carbon bond, okay. And then if you rotate 180 degrees, okay. So you generate kind of same molecule. That means here these two hydrogen, okay, are related by this rotation axis, okay. So if there's if you rotate 180 degrees, okay, so get different molecules. That's not rotation axis, okay. So that's how do you determine rotation axis, okay. All right. Okay. So this one is the symmetry plane actually pass kind of fluorine, carbon, chlorine, okay. Somehow hard to draw it, okay. So one hydrogen on your left, one hydrogen on your right, okay. So this simply plane just pass through this molecule, okay. So that's we call it a simply plane, okay. So all right, good, okay. So next kind of more kind of example, okay. So those bunch of molecule, okay, all related by kind of simply plane or rotation axis, okay. And then give only one signal, okay. So for the first one, okay, so the 2C3, okay, same chemical shape, okay, and then related by kind of the simply plane, okay, also rotation axis, okay. And then for this 2CH2, okay, related by simply plane and also rotation axis, okay. So that's the same chemical shape, okay. And then for the cyclopentane, okay, all the 10 proton, okay, 5 the CH2, okay, have only one signal, okay, because they related by kind of the rotation axis, simply plane, okay. So rotation simply plane, okay, here, at least here, okay. So all kind of same, okay. And same thing for the last one, okay. So last one, O4C3, okay. Related by kind of simple plan, also rotation axis, okay. And then they have kind of same couple shape. Yeah. So that's here the example here, okay. Right. And here are more example, okay. So this bond kind of showed more than one chemical shape, okay. So first one, okay, this C3 and this CH, okay, definitely have different chemical environment, okay. So yeah, they have kind of two signals, okay. All right, and then for this cyclopentanol, okay, so yeah, these two, okay, this CH2 will show one signal, okay, and then these two, okay, will show another signal, okay. So relate to kind of the simple plan or rotation axis, okay, something like this, okay. All right, and then for the this alkene molecule, okay, so yeah, the protons, okay, this proton different from here, okay, because this one close to chloride, okay, this one close to methyl, okay, plus this metal, okay, you should see kind of totally three signals, okay. All right, and then okay, so for this cyclohexene, okay, so yeah, show three signals, okay. So this will be one, okay, so this two proton will be same, okay, and this CH2 will be same, two, and then another CH2 will be same, okay, three, okay. Rotation axis simply plan castle like this way. Okay. All right. Okay. So now it's you guys here take try. Okay. Try to work on these three molecules. Okay, and then tell me okay how many proton signal you should see for the three guys. Okay. So if you like, you can also use annotation. Okay. So label like I did here. Okay. 1, 2, 3, 4. Okay. Or if you like, you can just type in the chart window. Okay. So A has kind of 4, 5 kind of signal. B has kind of 3. Okay. Maybe C has kind of 5. Okay. Right. Okay. Take a try. Okay. Yeah, practice on it. Okay. So that's kind of important thing. Okay. So you have to learn it. Okay. So you have to learn it. Okay. How to start? Okay. All right. Okay. So try to okay. So yeah. For example, okay, so yeah, for this 2C3, okay, 2C3, okay. So yeah, they relate by kind of simple plan and the rotation axis, okay. So that means this 2C3 will have same signal, okay. Okay. All right, similar thing kind of for this CH2 here, okay. So that's 2. Okay. So that means the butene has only 2 signals, okay. So yeah, don't get confused by kind of the curving bond here, okay? Because you can rotate this bond, okay? Right, and then that's simple plan rotation axis, okay? 2, 2, 1, 1, right? Okay. So I already told you guys kind of how many signals you can see for the A, okay? So yeah, take a try, okay? How many signals you can see for B and C, okay? Yeah. So one important kind of the technique, okay? So yeah, okay. So someone come up. B, okay. Any other answers, okay? All right. Cool. Okay. That's right. Okay. B should have the 2 signals. Okay. B should have 2 signals. Okay. How about C? Okay. Yeah. So one important kind of technique you have to learn is in future, if I give you one molecule, okay, you should quickly identify how many proton signals you should see for this molecule, okay? Yeah, that's very important technique, okay? Right, so for B, okay, so why is 2, okay? Because there's one proton connect to the center hydrogens, okay, so that's 1, right? And then all the 3 C3, okay, show same chemical shapes, okay, because they're released by the rotation axis simply plane, okay, so yeah, 2, 2, 2, okay. So for B, also 2, okay, right? Anyone want to try the C? Okay, how many signal we should see for this one? 1 or 2 or 3 or 4 or 5 even. Right, someone said 2, 3, 3. Anyone get more than 3? All right. Okay. So this is a little bit hard one. Okay. So the right answer should be full. Okay. Full. Okay. All right. So first, okay, so yeah, there's no symmetry plan for this, the symmetry plan rotation axis for this C3, okay, so that should be 1. And then there's only one CH2, okay, so definitely kind of okay, another one, okay. Right. There's one hydrogen on this carbon, okay, so that's give you 3, okay. In the end, okay, these two methyl group, okay, give same chemical shape, they have same chemical environment, okay, so symmetry, really by symmetry plan rotation axis, okay, so that's the 4. All right, so this is kind of relative hard one, okay. So yeah, but here with more practice, okay, you guys should be able to do it, okay. Yeah. Number 4 on the carbon, okay. So this CH2, okay, C3, okay, C3, okay, have same chemical shape, okay. These two, okay. Yeah, reason for that kind of related by kind of symmetry plan or rotation axis, okay. So you can think about kind of the here, okay. This one connect with the S group, okay. So don't confuse by kind of the bond, okay, because this bond can rotate the all the time, okay. So yeah, average out, okay. So that's if you think about just the S group, okay. So yeah, these two relate by rotation axis symmetry plane, okay. So that's why these two have same chemical shape, okay. Right, so that's the one way how do we determine kind of chemical shift, okay. So second way we do it kind of I call it replacement the method, okay. Replacement method kind of if you have two protons, you want to determine whether kind of same chemical shape or not, okay. So you replace the one proton with the one atom, okay, each time, okay, and then eventually you generate kind of two molecules, okay. So here like this, okay. So if you for the first example, if you replace the two proton each time with one atom or kind of the maybe letters, okay, then two molecule. These two molecules are same, okay. So yeah, these two definitely same. You rotate kind of 180 degrees, okay. Then we call them identical. Then these two proton have same chemical shape, okay. So if you replace the two atom each time with one atom, okay, with another atom or kind of letters, okay. And then generate two molecules. These two molecules are enantiomers, okay. Then these two protons also have same chemical shape, okay. Yeah. So yeah, identical, okay. So we call the homotopic kind of proton, okay, homotopic hydrogen, okay. And then enantiomer, okay, we call the enantiomer-topic hydrogen, okay. So those two kinds of hydrogen, okay, we call kind of the chemical equivalent kind of same chemical shape, okay. But if you replace the two hydrogen each time with another letter, okay, and then generate kind of two diastereomers, okay, then these two protons won't have kind of same chemical shape, okay. So for example, show here, okay. So this we compare this two red the protons, okay. Each time we replace with A, okay. So we generate kind of the two molecule, okay, and then we compare the relationship, okay. So typical this one kind of cis. This one trans, one cis, one trans cis isomers, the diastereomer topic, okay. So that's will belong to kind of the different chemical shape, okay. So different chemical shape, okay. And then for this molecule, okay, all three protons show different chemical, okay. So that's the right. So just keep in mind, okay, diastereomer topic kind of proton are not chemical going to show different chemical shape, okay. And then last one kind of continuous isomer, okay. So that's a pretty easy, okay. So for example, this molecule has two protons, okay. Each time we replace one proton with one letter X, okay, we generate kind of two molecule, okay. So these two molecule continuous isomer, okay. So they definitely kind of have a different chemical shape, okay. Right. So for you guys, okay. So the method 2, okay, just keep in mind, okay. So little bit hassle, but actually kind of pretty good one, okay. So if the two molecule generate kind of at the enantiomer, okay, or identical, okay. Then this two proton will have same chemical shape, okay. Same signal, okay. So if you generate kind of the diastereomer, okay, and the constituent isomer, okay, then you have different kind of chemical shapes, okay. So you should have kind of two different signals, okay. So that's yeah, please keep in mind. Okay, so that's why in chapter yeah 7 we did a lot of practice. Okay, as you guys kind of determine the relationship between these two molecules, enantiomer, diastereomer, or kind of identical, or kind of conjugacimer. Okay, so actually kind of real applications here. Okay, help you identify whether these two protons same composition or not. Okay, all right. Okay, so in the end, okay, so that's kind of important. Okay, so yeah, so if we come to CH2, okay, so if we two proton, okay, on the CH2, okay, so yeah, there's no chiral center, okay, so no steric centers, okay, in one molecule. These two proton will have same composition, okay. Example showed here, okay, so here, okay. So for this molecule, okay, there's no chiral centers, okay. So the two protons, okay, on the same carbon, okay, so same CH2, okay, have same composition, okay. But if there's the chiral center in the molecule, okay, the two CH2 will have a different chemical shape. Okay, so yeah, that's actually kind of not hard to understand. Okay, remember diastereomer, you will have kind of a different chemical shape. Okay, for this molecule, okay, so we do the replacement again. Okay, so yeah, we replace the one proton with probably the letter A, okay, each time. Okay, right. So for example, okay, we replace kind of the wedge bond kind of hydrogen with the A, okay, and then next, okay, replace the dash bond kind of replace kind of also wedge bond, okay. So this time we wedge bond replaced by A, okay, and then dash bond is still keep H, okay. So each time we replace it by one letters, okay. All right, okay. So then you look at the relationship between these two molecules, okay. You find kind of they are diastereomer, okay. One steric center, same. Another steric center, okay, opposite, okay. So yeah, one cannot connect wedged by hydrogen, dash by H, okay. This one wedged by A, okay, and then dash by kind of H, okay. So that's diastereomer. Diastereotopic, okay, so these two hydrogen have different chemical shapes, okay. Right, and also if we are any situation, okay, CH3 always shows same chemical shape. All three proton, okay, on the C3, okay, show same chemical shape. Even kind of you attach kind of chiral carbon, okay, all C3 kind of proton, okay, show same chemical shape, okay, because you quick rotate this bond, okay, so that's C3 can average out, okay, so show same chemical shape, okay. Similar thing for the T-butyl group, okay, okay, so the 9 hydrogens, okay, so 3 C3, okay, also show same chemical shape, okay, so even bound to kind of chiral carbons, okay. Same chemical shape, okay. That's please remember, okay. Those kind of very important information, okay. All right, okay. So yeah, that's we done the class today, okay. So yeah, we'll continue this chapter on Monday, okay. Yeah, any questions? Yeah, have a good day. You too, okay. Thank you. Yeah, thank you. Yeah, you too.